All right, welcome class. Here are lecture 9, beginning a new module, a new sequence of lectures where we will shift our attention away from the response of static perturbations, the response of systems to static perturbations, and begin a discussion concerning how systems respond to time-dependent perturbations. This requires us to start, however, with a discussion of what it means to talk about time dependence within an equilibrium system. Typically, one considers an equilibrium system as a system in which there is no time dependence. The stationarity of an equilibrium distribution, the time translational invariance of such a system, suggests that how we go about decoding dynamics from such statistics is subtle. Indeed, we will leverage a lot of the insights we gathered in discussing fluids or disordered systems, those with translational invariance, and you might begin to anticipate that what will be useful in our discussion are notions of correlation functions in decoding or in encoding the dynamics of a system evolving within an equilibrium ensemble. And you might also anticipate that such correlations will encode responses of systems to time-dependent perturbations. So today, I want to first reflect back on some of the lessons learned in the static case very briefly, just to kind of really summarize what we've seen there. And then I will launch into a discussion of classical mechanics, some basic statements that we can make about how distributions evolve in time, not just how particles evolve in time, a la Newton or Hamilton's equations of motion, and give some plausibility arguments for why we should expect that just under the action of a Hamiltonian, a Boltzmann distribution might emerge. This is specifically encoded in something called Liouville's theorem, an equation of motion for a probability density for which we can show the Boltzmann distribution is a stationary state of. Okay, but a first recap, just to kind of summarize what we've done thus far. We've learned that even microscopically, fluctuations encode response. This is true macroscopically. We know things like the heat capacity or the change in energy with changing temperature is given by the fluctuations of the macroscopic energy, the total system energy. But now we know similarly that if I wanted to ask a more microscopic question, like what is the average position of a particle in a potential, it is given by, at 0th order, where it was in the absence of some force, and applying some force F, that change in position is encoded by the scale of fluctuations of that particle in the absence of the force. Writing this differentially, the change in the particle position with some applied force is equal to a scale of fluctuations given by kBt times the fluctuations in that particle position. So fluctuations on the right encode response on the left. We even further developed this prescription or this perspective, thinking somewhat abstractly, not in terms of particles themselves, but in terms of the fields that they generate. So if this was a particle view, a field theory view could be summarized as, imagine I take a density field and ask how it responds to an applied external potential. Well, to 0th order, it's the density in the absence of the field, and for a fluid with translational invariance, that density is just the bulk density. And the 1st order correction is determined by how the density, the absence of the perturbation, depends on that applied field times the strength of that applied field, which we found was given by a density-density correlation function. So when we go to high dimensional responses, the responses of a whole field, we consider not just simple fluctuation quantities, like the fluctuations in just the position, but now correlations are how fluctuations depend on one another. This is an object we called chi, and it encoded, for example, the fluctuations in the density or other fields. In fact, the last couple lectures, we've generalized this prescription away from just density fluctuations to fluctuations of the height field for a membrane, or the phonon field, the displacement field, or just polarization field associated with solvating an electron. Finally, we employed the framework of Gaussian field theory, in which we describe the statistics of some collective variable field through a Gaussian functional. Like this, for example, in the density field, which, noting that Gaussian distributions are uniquely specified by their two cumulants, the mean of the field and its correlation function, provided a route for a self-consistent theory that would allow us to determine that correlation function. So the development was noting first that fluctuations encode response, and in high dimensional systems, correlations replace simple fluctuations, and then acknowledging that those correlation functions played such a central role, we went down a bit of a path trying to figure out how to write down a theory for which we could then solve for what those correlation functions are, or model what we expect those correlation functions to look like. And that generically is a Gaussian field theory, for which we've now shown a couple examples. Essentially, our discussion of time dependence will follow a similar course. We'll note that fluctuations now of dynamical variables encode response to time-dependent quantities, and then seeking or understanding an important role or a central role that time correlations, or simple measures of those fluctuations, encode response, then postulate models for which we can solve, or effective theories for which we can solve for those correlation functions. They will depend or be underlined by Gaussian random processes like we've done before, and will go by names like the Langevin equation or Redfield theory, whether or not you're taking a classical or quantum mechanical perspective. However, before we get quite there, we need to build a little bit of intuition about time dependence and equilibrium and remind you a little bit about mechanics itself. And that, first and foremost, requires us to bring back a quantity that we have largely neglected in the discussion thus far, and that is the momentum degrees of freedom, which through the independence of momentum and configurational variables at equilibrium for static quantities, we've not needed to pay any attention to, absent quantum mechanical cases where those two operators don't commute. But certainly through the equations of motion, both variables are correlated in time, and thus we need to remind ourselves a little bit about how to manipulate or how to think about a space for which is defined over both those momentum and configurational variables. Okay, so that brings us now to our Introduction to Time Dependence in Thermal Equilibrium. Okay, so first, for a classical system made out of particles, I know from introductory material what the probability associated with seeing an individual microstate of the system is, if that microstate is specified by a set of positions, r to the n, of all n variables, and a set of conjugate momentum, p to the n. Let's define that probability density on the space of phase space with an F, and denote its equilibrium value as FEQ under equilibrium conditions, holding things like the temperature, volume, and number of particles fixed. The probability of seeing that microstate is just Boltzmann distributed, provided a Hamiltonian that depends on that phase space point. And for particle systems described by a phase space point, most often that Hamiltonian has two pieces: a kinetic energy piece, which is given by a sum of the momentum of each particle squared, divided by twice the mass of that particle. Assuming all particles are the same, I won't index the mass. And in general, a potential energy function, which is maybe not so separable and depends on the total configuration where all points are relative to each other at one time. Often that potential does not depend on the absolute positions of particles. Nevertheless, it is a function of all of them. We're reminded that it's the linearity and the separability of the kinetic energy from the potential energy that generates the statistical independence of momentum fluctuations from configurational fluctuations. Okay, so that is the distribution of phase space points, the likelihood of seeing a microstate of the system in a Boltzmann in an equilibrium case. And often we assume that it's through that distribution that we can compute averages. However, one might have expected that if I have a dynamical system, that average, an average over the Boltzmann distribution, is not necessarily a unique definition. I could imagine different sorts of averages. In fact, they essentially boil down to two primary kinds of averaging that one can do in a dynamical system. One's over that distribution and over some finite time. So a time average or a so-called ensemble average. We will deal with both in the subsequent lectures, so it behooves us to define both carefully. A time average, let's denote with an over bar, and let's consider a specific case where I want the time average of the position of particle I what one means by that is to take that dynamical variable, r of I, as a function of time, and follow it up to some observation time. Call it t-obs. So that's a time average. Now, what does that average actually encode? To evaluate that average, I need to know the time dependence of Ri. The time dependence is encoded by an equation of motion. For example, given the Hamiltonian, I can evaluate the time dependence. The time derivative of Ri is given from the Hamiltonian as a partial derivative of that Hamiltonian with respect to a conjugate momentum, pi. That is not closed because the Hamiltonian depends on both Ri as well as pi. And so I need an equation of motion for pi. Those are total derivatives. And that's given by a minus the gradient of the Hamiltonian with respect to the conjugate position. So these are two coupled equations, which if I could solve, would provide me the dynamics Ri going into that average. Some of you might not be super familiar with writing down equations of motion in this Hamiltonian form. But they are identical to those Newtonian equations of motion. dr dt, the derivative of the Hamiltonian with respect to the momentum, well, that pulls out the momentum of particle I. I get a factor of 2, canceling the factor of 2 in the denominator, and a mass underneath. That is, in fact, just given by the velocity, the usual quantity entering into the rate of change in time of the position from Newton. And analogously, the rate of change of the momentum of particle I is given by the gradient of Hamiltonian with respect to Ri, which just gives me the gradient of the potential up to a minus sign, or the force acting on the particle. That's a way of just saying that F on the right is equal to ma mass times the acceleration. Now, these are two first order coupled differential equations. They are uniquely specified, therefore, by a single boundary condition. I could choose that boundary condition to be an initial condition. And should I be able to solve both of those, those coupled sets of equations for all in particles, the positions and momentum, I could arrive at the time dependence of Ri, which is then a function of all in particle positions up to time t, and all in momentum up to t. But given the unique mapping from that set of equations and initial condition, you can think of Ri of t as being completely determined by a parameter t, how far I wait from some initial conditions, some set of initial positions and momentum. So a time average encoding the dynamical evolution of some variable is formally given by just a set of initial conditions in the full phase space, some initial microstate given by all initial configurational degrees of freedom and all their corresponding momentum. That then takes us to a second kind of average. So apart from a time average, we can consider a so-called ensemble average. As usually denoted with a bracket. As being given by an integral over those initial conditions. So the different kinds of averages are either following a particle over a single trajectory through time, or drawing a different set of initial conditions and evolving each one of those initial conditions up to some time t. Now, if this is an equilibrium distribution, we will see shortly that that implies a stationarity, which means that that Ri averaged of t is independent of that label t, and thus equal to any other t, like the 0th t. Now there is an assumption known as the ergodic hypothesis, that as t goes to infinity, or t obs goes to infinity, that the time-dependent average is equal to an ensemble average. Namely, if I follow a trajectory long enough, it visits states in proportion to its Boltzmann weight. Why would that possibly be the case? So, excellent question. Very hard to prove the ergodic hypothesis. For systems that are simple enough to study and analyze in detail, they often do not obey an ergodic hypothesis. However, for complex systems, one finds that there is sufficient chaotic dynamics that causes sufficient mixing in phase space that this is indeed true. Underlying a Boltzmann distribution is an assumption that at constant energy, all microstates are visited in equal proportion. It's just then opening up that system as a subsystem that we get a Boltzmann distribution, or a energetic preference for low energy states. And thus the requirement here is that under the evolution of a Hamiltonian system, that all microstates for a full closed system are visited in equal likelihood. So that then maybe you can imagine follows from a sufficiently chaotic dynamics. But those sorts of statements are fairly hand-wavy and vague, and not super satisfying. So the best one can do is to provide a plausibility argument for why these averages should be equal, and why statistical mechanics really does follow, equilibrium statistical mechanics really does follow from dynamical systems, from the evolution of a classical system under its Hamiltonian. So to give you that plausibility argument, we have to first derive a result known as Liouville's theorem, which is a statement about how distributions defined on phase space evolve in time. Okay, this discussion is essentially a question of how exactly we create a map for a set of initial conditions to their time-evolved position, given that unlike Laplace's demon, we don't have infinite computing power. We cannot simultaneously solve a very high dimensional system arbitrarily precisely to actually execute the coupling or to understand the coupling of all those ordinary differential equations that Newton or Hamilton supplies us. In fact, that's the kind of detailed information we, having worked through many examples now, classical statistical mechanics, expect to not really be so relevant. We don't really usually care about all the microscopic detail, the individual microstates, or in this case, how they evolve in time. What we really care about is how their statistical properties evolve. So one aim, you can imagine, might be to, that should be T, you might imagine trying to ask about how does the distribution of these points evolve in time, even if the exact map is maybe too difficult to get our head around. So let's consider explicitly the time dependence of some distribution of points in phase space. Let's denote phase space as X, and it's that set of n positions and n momentum. For an arbitrary distribution, not an equilibrium distribution, let's denote that distribution F, no subscript, and its time dependence is given by just the time derivative of F. Now there are two contributions to that total time derivative. There is how F itself might change in time, but in addition, through the action of the equation of motion, those points also have a time dependence. And so through the chain rule, I have a time dependence of the point in phase space and how that point changes the distribution following from the gradient of that distribution of that phase space point. Unwrapping this, the first term is as simple as we can write. The next term would be a sum over all components of that phase space point, the momentum, and how it affects a change in F, plus the position, and how it affects a change in F. This total derivative is known as a convective derivative. It naturally breaks up into those two pieces, which says both how that distribution itself changes and how the points making up that distribution change. So the time dependence of the density itself, df d partial f partial t, can be understood by considering a volume in phase space, call it V, and how the number of points in that phase space change as a function of time. So df dt integrated over that volume. Well, if the number of points are changing and that volume is incompressible, it is spanned by a set of points that can either come in or out, but not can be created or destroyed. I don't create new positions or new momentum. For that density to change, it must be that points enter in or out through a surface. We can define the normal vector to that surface as n. And thus the total change within any arbitrary volume V is given by an integral over a surface, the dot product of that normal vector with the flux of points given by the current of x times f. From the divergence theorem, assuming those points are indeed incompressible, we can write that this is a volume integral now over the gradient of that current. Anyone unfamiliar with the divergence theorem from vector calculus should go and look up Yoon's discussions. You discussed it last week in anticipation of this lecture. So this is true for any volume V. And so we can equate the arguments under those integrals, df dt partial f partial t, thus must be equal to minus the gradient of this current. Expanding that out, we have minus the current times the gradient in f, and minus f times the gradient of the current. In a per component writing, that's minus p dot df dp plus r dot df dr plus dp dot dp times f and dr dot dr times f. This can be simplified noting Hamilton's equation of motion. Written above, inserting that in the second two pieces. P dot is nothing but dh dr with a minus sign. R dot is nothing but dh dp assuming the Hamiltonian is a smooth function, so the order of the differentials doesn't matter, that sum is then identically 0, leaving us with minus x dot grad f as df dt. So that is to say, if we go back up to our total derivative, df plus x dot grad f, that means that the total derivative of f with respect to t is 0. This is a complicated way of saying, under Hamiltonian mechanics, total f is 0, or that probability is conserved. A Hamiltonian system conserves the probability. If I start with a probability distribution, I act on it through the evolution of a Hamiltonian, then that probability stays conserved. And this should make sense. It's a physical operation. I'm not doing anything from outside, just like the conservation of norm of a wave function under the action of a Hamiltonian, this distribution of phase space points is conserved. This is indeed then Liouville's theorem, that partial f partial t is minus x dot grad f, or that total f d dt is 0. All right, so that's all well and good. That tells us that probability itself is conserved, but the form of the distribution may change. In fact, we've now gotten an evolution equation for how that distribution changes in time. But this highlighted equation tells us how we evolve that distribution. df dt as a linear equation can define a linear operator, call it script L, acting on f, where L is equal to, in a per component writing, p dot d dp, so it's a differential operator, plus r dot d dr. This is a simple equation to solve in principle. F evolved to some time t. It's a function of phase space, is just given by the exponential of the Liouvillean operator, script L times t, acting on some initial condition. We will see shortly that the action of L on a function of phase space, not the probability distribution, takes a slightly different form. If I have some function of phase space points, some operator A, its time evolution away from some initial condition is given by the action of the Liouvillean operator with a positive sign in the argument of the exponent, not a negative sign. This will follow from an integration by parts, and we'll see that shortly. However, going back to our equation with our differential operator, we can note that an equilibrium distribution f takes the form of an exponential of minus beta, the Hamiltonian, where we could make it an equality through some partition function. Let's call it Q. And now note what the action of this evolution operator is on the equilibrium distribution. L acting on F EQ. Well, from the chain rule, I will pull down a minus beta. I will get the distribution back. And now I will have the action of that differential operator on the Hamiltonian, which is a function of those phase space points, dH dP plus R dot dH dr. Noting that we can write P dot and R dot as itself differentials of the Hamiltonian, that action of L on the equilibrium distribution is given by minus dH dr times dH dP plus dH dP dH dr. And what have we just found? That the action of the Liouvillean operator on the equilibrium distribution leaves it invariant. So F EQ is a steady state. So indeed, Hamiltonian mechanics naturally can generate a Boltzmann distribution. It is a steady state in the phase space. It is not a unique steady state. That's hard to prove. Uniqueness is hard to prove. However, it is possible that that distribution emerges from the action of this linear operator on the phase space points. So given a set of systems and a set of initial conditions, it is plausible, or it is possible, that a Boltzmann distribution emerges. Stationarity does require, it does, as you can kind of see, it needs to be some function of the Hamiltonian to be invariant. And it's hard actually to come up with other forms other than this exponential form and linear in the argument of the exponential of the Hamiltonian that satisfies stationarity, and additionally, things like extensivity of the entropy or energy. With those constraints, it's easier to argue for the uniqueness of this distribution, but still not entirely rigorous to do so. Okay, so this operator, Liouville's theorem, defined through Liouville's theorem, gives us a sense in which we can talk about the dynamics of a probability distribution, which then lets us talk about if we're talking about ensemble averages, we can now use this to define time-dependent quantities as ensemble averages over time-dependent distributions. This brings us to a discussion of time correlation functions, because we will see that through Liouville's theorem, it's straightforward to prove the time translational invariance of simple averages. Okay, so let's go back to that ensemble average of the particle position at time t. As an ensemble average, it's an integral over the phase space. some distribution of points and say that this is an equilibrium distribution. And the observable R of t. That is uniquely determined by an initial condition and the time dependence of that distribution. Let's not do equilibrium quite yet. So that would be one way to compute it. I start somewhere and I evolve the probability distribution at different times. So this is just some, not even really right to give it time dependence. It's not, it's just an operator whose average over a time-dependent probability distribution gives me a time-dependent average. So I can, through Liouville's theorem, pull out the time dependence of that distribution. And noting that L is a differential operator, I could integrate by parts and defining the boundaries of f at plus and minus infinity to go to 0. There are no boundary terms. I can move the action of that operator over to R at the expense of a minus sign. And thus it is reasonable then to define the time dependence now in R. And thus we see that the so-called anti-self-adjoint nature of the Liouville operator in that its action on functions of phase space, operators in the phase space, is to change the sign of the exponential operator, while the action on the phase space density comes in with a minus sign. This is very different from the adjoint operator, adjoint evolution operator in quantum mechanics, whose action to the left or to the right is the same. So noting that, if we had an equilibrium distribution, taking that last line but putting in that this is an equilibrium distribution, we can pull that operator back out, act it over on the right instead through an integration by parts. And now the fact that the equilibrium distribution is stationary under the action of L leaves that F time independent. And thus the average of R at T in an equilibrium distribution is identical to the average of R at 0. This is a demonstration of time translational invariance. An equilibrium distribution is one in which there is no unique time. All times are equal because the distribution is not changing in time. So what I decide to call the origin of time is arbitrary. So a simple expectation value of a single time does not itself encode any time dependence. We have to go to a higher order object to do so. And that brings us to a discussion of time correlation functions. So for example, I could define an average of some operator A at time 0 and an operator B at time t. Now there's a non-trivial dependence on what time I'm looking at. If I pulled out that Liouvillean operator, brought this now to B at 0, an integration by parts acts A, or the anti-self-adjoint nature of the Liouvillean operator, then acts on A by changing its sign, rolling that back into the observable A, I find that A has been changed to not being defined at 0, but it being defined at minus t. So the stationarity lets me talk about observables relative to each other in time, but if they're not taken at the same time, there is a non-trivial time dependence. I'm free to choose an origin of time, be it 0 or minus t, as I like, but provided I'm looking at two different times, there's non-trivial correlations encoded in such an operator. So time correlation functions, of which this is an example, are somewhat simple. If I evaluate that time correlation function at t is equal to 0, so A at 0, B at 0, well, now they're evaluated at the same time. That is just some different operator, equilibrium averaged. And in general, something finite. However, in the opposite limit, as t goes to infinity, one might expect that A and B become uncorrelated. So if I go long enough in time, the system doesn't matter, or for B, the fluctuations in B are insensitive to whatever happened at A at the origin of time. I'm then averaging two other variables independently, so those are just a product of equilibrium averages. So a time correlation function goes between a correlated average to an uncorrelated average. And so we can see that loss of correlation encodes relaxation. How a system changes in time, how it relaxes from some initial condition, is encoded by the loss of correlations between variables. Okay, so for the remainder of the lecture, I want to talk about a concrete example of these ideas in a system that we will revisit a couple times over the course of this section. So what I want to envision is a particle moving around in a solvent. So let's imagine we have some solvent. We won't need to prescribe any structure to it. And in that solvent, there's a particle. that can undergo some motion. Oh, that's very ugly. So it might start somewhere at time 0 and end somewhere else at time t later. So if I wanted to understand where that particle goes, I know in principle I just need to solve this equation, dr dt is equal to v, which I can integrate. Integrating the left side, I get r of t less some initial condition is given by the integral of the velocity up to that time. Now, of course, to know exactly where the particle goes, I need to know the time series of v. However, I can ask simple things like, if the system is in equilibrium, what is the average value of this displacement? The linearity of averages allows me to bring that averaging operation inside. And now the average velocity, if this is an equilibrium average I'm taking, the Maxwell-Boltzmann distribution in the stationarity of equilibrium says that stationarity says first I can take that average at any time I want. And the Maxwell-Boltzmann distribution tells me that that average is identically 0, which means that absent anything else, a particle in a solution doesn't go anywhere on average. There's no net, or more precisely, there's no net direction to that motion because there's no net velocity that persists. That is essentially a statement of symmetry. The fact that the average velocity has to be 0 is essentially saying that the only way I could get a persistent velocity is if particles were flowing. That would violate an equilibrium assumption. That doesn't mean that particles really don't go anywhere typically on average. We could get some more insight into the particle motion by considering not the average displacement, but its mean squared displacement. So let's define delta R as the displacement of the particle over time. Now let's imagine that that displacement, I could discretize this integral into some sum tau long of little hops, call them delta R, little displacements, little integrals over time, lasting a duration tau. Delta R squared is then given by squaring that sum. I introduce a dummy index j. And now I have 2 of these little displacements, each in tau length, which I can decompose into self terms and non-self terms. And on average, the mean squared displacement, I could bring the averages inside. I get something like t over tau delta R squared some little displacement, plus a correlation between hops at different times. Now, for long enough times, those correlations between little displacements should vanish. So as long as there aren't n squared number of terms in this, we have just argued that the mean squared displacement should go proportional to just the self-term, something proportional to t. For short enough times, however, the mean squared displacement, going back to our velocity integral, if the time is very short, maybe there's no time for that particle to bang into anything, it will then, so if there are no forces acting on it, it would move ballistically. The mean squared displacement thus goes like the mean velocity squared times t squared. Again, if this is a Boltzmann distribution, the mean squared displacement is just kbt by m with a factor of d for dimension and t squared. So putting these two results together, the mean squared displacement as a function of time is going to go initially quadratically, but asymptotically linearly. The slope asymptotically we can define as twice a constant capital D times little d, the dimensionality, where that capital D is known as the diffusion constant. So at long enough times, one can read off that slope by dividing by t. And this defines a constant, a diffusion constant. Why should we call that a diffusion constant, a variable that encodes how particles move through the solution, noting that they don't move anywhere on average? Well, that diffusion constant is a phenomenological number that is a material-dependent property of a solution, and specifically of a solution in which there's a concentration gradient. So diffusion constant is defined through Fick's law, a law that tells me how how concentration gradients change over time. It is also a conservation equation. Given mass is conserved, the change in the mass at some point in space and time is given just by the second derivative of any concentration gradient over time. Let's call this R. So this is the concentration of particles at R and T, which we know microscopically refers just to the probability that a particle is somewhere. That's what microscopically a density means. Using the interpretation as a probability, we can define an expectation value of delta R squared as an integral of that probability distribution at some time, taking its time derivative well, its time depends on that probability distribution. Inserting Fick's law gives me a factor of that diffusion constant. And a couple integration by parts. Finds that indeed that mean squared displacement is phenomenologically the same in a dilute solution where I can associate a single density, single particle density, as the phenomenological diffusion constant. And again, assuming that the concentrations go to 0 at plus and minus infinity. Now, an alternative description of diffusion would be to consider the equation of motion from the velocity side instead of the displacement side. So delta R squared and averaged is from our equation of motion two integrals over the velocity or over time of the velocity, which gives me now a correlation function that encodes how velocities are correlated with each other. The stationarity of an equilibrium average, like I've denoted in the bracket, implies that I could rewrite that time correlation function as the average of V at 0 and V at T double prime less T prime. And thus we find that that correlation function again just depends on times relative to each other. If we define tau as T double prime less T prime and T bar as T double prime plus T prime, we can do a change of variables in which we move along. So initially we explore a box that goes from 0 to T in both T prime and T double prime. That's the area under the two integrals. We can take a cut through that box where T double prime is always greater than T prime. That will come with it a Jacobian of 2. And thus we can rewrite this as twice 0 to t of tau integral 0 to t minus tau dt bar v0 v tau, and can integrate exactly that first integral. And in the limit that t goes to infinity, we know that phenomenologically this is related to our diffusion constant. We can simplify this. So if t goes to infinity, as long as that correlation function decays fast enough, it will be dominated by the thing linear in t going to infinity. Dividing by d, we find that the diffusion constant is equal to an integral from 0 to infinity of that velocity-velocity autocorrelation function up to a factor of dimensionality due to these being vectors. That's a pretty cool result. The fluctuations or the correlations of the velocity encode a transport quantity, the diffusion constant. Again, this is done a little quickly. We'll describe these sorts of things in much more detail, but this is an example of a so-called Green-Kubo result, a time correlation integral given a transport quantity, and was first derived by Einstein when he was thinking about Brownian motion and diffusion therein. So there's just one example of many of time correlation functions encoding response, in this case, the response of a concentration gradient. Okay, so that's kind of, a little bit of a teaser for where we're going now that we have this notion of how to think about time dependence. Our next lecture will be a little bit of an aside on molecular dynamics simulations, a tool and a corresponding framework for which we can imagine simulating time-dependent properties in a way we haven't been able to with simple Monte Carlo simulation techniques. And then we'll return back to a discussion of response theory, and in this case, time-dependent response. So I'll go ahead and end a little early today, give you back some of the time I borrowed from some of the previous lectures, and I'll look forward to seeing you all in the small group discussions, and I hope you all are well.